Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on analytical dynamics or classical mechanics, chapter constrained motion, lecture number 3, in which I will discuss about degrees of freedom and generalized coordinates. Now, we wish to know what is the meaning of degrees of freedom of a dynamical system, or what is the number of degrees of freedom of a dynamical system. Firstly, by an example, we would like to clarify this. The motion of any particle may be described by its three coordinate x, y, z. The particle may move in any manner. So it has 3 degrees of freedom. Means it may freely move in 3 dimensions. If we restrict the motion of this particle by giving z equal to 0, that means the particle is restricted to move in xy plane, then 1 degree of freedom is seized. So remaining number of degrees of freedom will be 2, and in this case the motion of the particle will be described by 2 coordinates x and y. These 2 coordinates are independent. X and y are independent coordinates to describe the motion of the particle in this case. So the number of degrees of freedom will be 3 minus 1, that is 2, and these 2 degrees of freedom will be described by 2 independent coordinates x and y. Now I would like to give the details idea, definition of degrees of freedom. The number of independent ways in which a mechanical system can move without violating any constraint. Here constraint was z equal to 0. Restriction was z equal to 0. So the number of independent ways in which a mechanical system can move without violating any constraint which may be imposed is called number of degrees of freedom. It is indicated by the least possible number of coordinates to describe the system completely. Here we have least possible number of coordinates to describe the motion of the system is 2, x and y, and so here number of degrees of freedom be 2. The number of degrees of freedom is equal to the number of coordinates minus the number of independent equations of constraints. Here in this case the number of independent equation of constraints is 1, and number of coordinates required for the description of the motion of the particle was 3 coordinates x, y, z, and 1 equation. This equation is constraint equation, and 3 minus 1 number of constant equation minus, so this remains 2. So we get 2 degrees of freedom. So here the number of degrees of freedom is equal to the number of coordinates minus number of independent equation of constraints. The configuration of the system of n particle is described by 3n Cartesian coordinates. Why? Because one particle requires 3 coordinates to describe its motion. For example, M1 be the first particle which needs x1, y1, z1 coordinates to describe its motion. Similarly, second particle requires other three coordinates x2, y2, z2. Similarly, n particles requires 3 multiply n number of coordinates. If the system is subjected to k independent constants expressible by k equations of the form f1, x1, y1, z1 for first particle, x2, y2, z2 for second particle. Similarly, xn, yn, zn for nth particle, and this function, value of this function equal to 0. By equation it is expressed. Similarly, another constant equation is f2, x1, y1, z1, x2, y2, z2 dot xn, yn, zn equal to 0. Similarly, fk, x1, y1, z1, x2, y2, z2 comma dot xn, yn, zn equal to 0. Here we get k number of constant equations. Total number of coordinates required is 3n, and here k number of constant equation. Therefore, number of degrees of freedom equal to 3n minus k. Now we give an example. Suppose that three particles are connected by rigid rods to form a triangular body with the particles at its corner. Here one particle, this is M1, second particle is M2, third particle is M3. All are connected by rigid rods. Let coordinates of M1 be x1, y1, z1. Coordinates of M2 be x2, y2, z2. Coordinates of M3 be x3, y3, z3. Here the configuration of the system is subjected by giving location of three particles each. Here each particle requires three coordinates. So second particle also requires three coordinates and third particle also requires three coordinates. So number of coordinates required is 3 multiplied by 3 equal to 9 coordinates. But each rod, rigid rod, is represented mathematically by independent equation. Let length of this rod, rigid rod, is L1, this is L2, this is L3. So x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square is the square of L1 square. This is constant, rigid rod, means length is constant. Similarly, x2 minus x3 whole square plus y2 minus y3 whole square plus z2 minus z3 whole square. This is L2 square, length of the second rod, and x3 minus x1 whole square plus y3 minus y1 whole square plus z3 minus z1 whole square equal to L3 square. So we get 3 number of constant equation. Since total number of coordinates required equal to 9, number of constant equations equal to 3, therefore number of degrees of freedom equal to total number of coordinates minus number of constant equations, means 6. Now we have a question. So that a rigid body has 6 degrees of freedom. By a rigid body, we mean that a rigid assembly of particles with fixed interparticle distances. Because in a rigid body, distance between any two particles be always same. So fixed interparticle distance. A rigid body with n particles can have at most 3n degrees of freedom. At most means maximum 3n degrees of freedom, because one particle requires 3 coordinates. Similarly, n particles requires 3n coordinates. So maximum number of degrees of freedom may be 3n. Since it has n into n minus 1 by 2 mutual distances between pair of particles. The distances are distance between m1, m2, m1, m3, m1, m4, m1, mn. Second, m2, m3, m3, m4 and so on. In this way we get mutual distances n into n minus 1 by 2. For rigid body, distance between two particles is always fixed. So we may get different constant equations with the help of these distances, and we know that number of degrees of freedom equal to number of coordinates, that is 3n number of coordinates minus number of constant equations, that is left side will be less than 3n. Let here we consider 3 particular particles m1, m2, m3 whose coordinates are x1, y1, z1, x2, y2, z2 and x3, y3, z3 respectively. Distance between m1 and m2 is L1, distance between m1 and m3 be L3, distance between m2 and m3 be L2. This may be written in the equation form: x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square equal to L1 square, x2 minus x3 whole square plus y2 minus y3 whole square plus z2 minus z3 whole square equal to L2 square, and x3 minus x1 whole square plus y3 minus y1 whole square plus z3 minus z1 whole square equal to L3 square. So here we get three constant equations. Total number of coordinates for three particles equal to 3 multiply 3, that is 9, and here 3 number of constant equation, equal to 3. Therefore, degrees of freedom of these three particles equal to 9 minus 3 equal to 6. Let us include particle M4. Here M4, coordinates of M4 be x4, y4, z4. It requires three coordinates. Therefore, maximum number of degrees of freedom of four particles may be, for three particles we have 6 degrees of freedom, and here three coordinates means 6 plus 3 equal to 9. But constant equations for M4 will be 3, because distances between M4 M1, M4 M2 and M4 M3 will give three equations, that is number of constant equations due to M4 equal to 3. Therefore, number of degrees of freedom of four particles equal to here 9 minus 3 number of constant equation, that is 6, same as number of degrees of freedom for three particles, which is same as number of degrees of freedom of three particles of the rigid body. Therefore, any other particle apart from M1, M2, M3 taken to specify the configuration of the rigid body will not add any new degree of freedom. Thus, configuration of the rigid body would be completely specified by any particular three non-collinear particles, that is by 6 degrees of freedom. Now we will describe about the idea of generalized coordinates. To describe the configuration of a dynamical system, we select the smallest possible number of variables. These are called generalized coordinate of the system. The generalized coordinates are denoted by q1, q2, qn. These coordinates may be distances, angles, or quantities related to them. For example, in dealing with rigid body motion, we specify 3 Cartesian coordinates x, y, z to locate center of mass with respect to external origin, and 3 angle coordinates theta, phi and psi relative to origin at the center of mass, that is 6 number of generalized coordinates. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.